alone. We assume that there are two space charge regions, one of the emitter junction and the other of the collector junction, and there are three neutral regions. The one of the emitter on the left, the one of the base in between, and the one of the collector on the right. At this point, we make some assumption about the extension of the neutral base region, W. We consider one possibility, which is not the correct one, but we consider it anyhow. We assume that W, that is the width of the neutral region in the base, is larger than LB, where LB is the diffusion length of the minority carriers of the base. So, for instance, if we consider the PNP type, then the base region is of the N type and the minority carriers are holes. So for the PNP transistor, LB is the diffusion length of the holes, that is the product, as you remember, of the lifetime times the diffusion coefficients under the square root. If we instead consider the NPN type, then the base is a P region and the minority carriers are electrons. So if W is much larger than LB, in essence, qualitatively, we can say the two junctions are very far apart from each other. And because of that, the two junctions behave independently from each other, which is reasonable. If the two junctions are very far from each other, each junction behaves as if the other junction does not exist. In this case, the bipolar transistor reduces to nothing else than PN junction put together. And you can see in the central part of the page, the inset, okay, shows what happens when the length W is very large. In the PNP case, the transistor becomes two PN junctions in which the N regions are put together. In the other case, the NPN case, the two PN junctions have the P regions put together again to form the base region of the transistor. So from the circuit point of view, in this case, the transistor behaves as two independent diodes. But this is the wrong structure. Nobody would design a transistor in which W is larger than the diffusion length, LB. Actually, the correct design is such, you can see it in the lower part. This is the correct design. We must still have a neutral region in the base, W, but this region must be smaller than the diffusion length of the minority carriers of the base. To better understand this, we can qualitatively draw a picture of the minority carrier concentrations. Okay, but before that, we make another observation. You see from this picture here that in the emitter region, the extension of the space charge region is somewhat small. Okay, OE minus is very close to OE, and OE plus is almost relatively close to OE. In contrast, if you look at the collector junction, you see that the extension of the space charge region is much wider. This is so because we assume that the device is functioning in the so-called normal mode of operation. And you remember that in the normal mode of operation, the emitter junction is forward biased. So the extension of the space charge region is small. And in the collector junction, the bias is reverse. So the extension of the space charge region is wide. Also, you see that if you look again at the emitter junction, the extension of the space charge region on the emitter side is smaller than that on the base side. And this is so because the concentration of the dopant in the emitter is larger than that of the base. And we shall explain why later. Similarly, the extension of the space charge region of the collector junction on the base side is smaller than that of the collector side, again, because the doping in the base has a larger concentration than that of the collector. If we now look at the distribution of the minority carrier concentrations in the two cases, so the upper part of the figure shows the situation when W is large, that is the unrealistic design of the device. You see that if you start from OE plus, the minority carrier concentration in the base decays exponentially or changes exponentially from the value at the junction, and you remember this value is prescribed by the Shockley boundary condition, to the asymptotic value. So there is an asymptotic behavior of the minority carrier concentration that essentially decouples the left and right part of the device. Instead, if you consider the proper design in which W is smaller than an LB, that means that W is essentially very thin. So the two boundary conditions are kept. They are the same as in the other example, but the behavior of the minority carriers is substantially different. Essentially, there is no asymptotic behavior. When the base is very, very thin, we can even linearize the distribution of the minority carriers, okay? So since the minority carriers have a decreasing, they decrease from left to right, we see that we expect that there is a diffusion of the minority carriers from left to right, okay? So we shall see this better with the calculations. At this point, what we do in order to find the characteristics of the bipolar transistor is essentially to follow a replica of what we did for the PN junction. We use the same hypothesis as for the PN junction, that is that in the neutral regions, the current of the minority carriers is essentially diffusive, so we can neglect the electric field. And also, we assume the weak injection condition So we take the linearized form of the net recombination term of the Shockley Reed Hall type. And by this, we not only achieve a linearization of the equations, but also we decouple the equation of the minority carriers. So instead of solving the problem in 2 regions, then we shall solve the problem in 3 regions, the 3 neutral regions, emitter, collector, and base. However, there is a difference, and the difference is that in the emitter and collector regions, as you can see in the upper part of the figure, we do have the asymptotic behavior of the minority carriers. So we have a boundary condition that is, in quotes, relatively easy to deal with. In the base, of course, we don't have any asymptotic condition because the base is thin, okay? So we have 2 boundary conditions at a finite distance from the origin, and we must account for both, okay? There is no asymptotic condition to use in the base region. So the calculations follow. We simply change the symbols. So we start with the emitter, and we consider the PNP type transistor, okay? We assume that the device is in non-equilibrium condition. That means that we have applied 1 voltage from the emitter to the base contact and another voltage between the collector and the base contact. In the PNP transistor, when we start, for instance, with the emitter region is doped of the p-type, so the minority carriers are the electrons. So what we seek for is a differential equation for the concentration of the electrons in the emitter. So x goes from minus infinity, which is the asymptotic condition on the left, to x to the position of OE minus that we take as a 0, as we did in the PN junction. We change slightly the symbol, so instead of writing NP0, we write N sub E. That means the asymptotic minority carrier concentration of the emitter. Of course, N sub E is given by Ni squared over capital N sub E. And the diffusion length of the minority carriers of the emitter, that in this case are the electrons, is L sub B equal to the square root of the lifetime times the diffusion coefficient. So this theory is identical to that of the left part of the PN junction. So we impose the asymptotic condition on n of minus infinity is N sub E. N at 0 is the Shockley boundary condition. So it is N sub B times the exponential of Q VEB over KT, where VEB is the voltage applied between the emitter and base contact. Then we proceed by calculating the current. The current is purely diffusive, so it can be written as QDE, where DE is the diffusion coefficient of the electrons, times the derivative dn over dx. And as we did in the case of the PN junction, we extract the coefficient Jn of OE minus, and this coefficient is written below. It is equal to Q, the diffusion coefficient, D sub E, N sub E divided by LE times the non-dimensional factor f of E, that is the exponential of QVEB over KT minus 1. So this is it for the emitter. When we go to the collector, the analysis is identical. There is only one difference. And the difference is the following, that we calculate the solution of the differential equation in which the asymptotic value is called N sub C, the diffusion length is called L sub C, the asymptotic condition is at plus infinity, and C and the condition at the edge of the space charge region is N of 0 equal to NC exponential of Q over KT times VCB. VCB is the voltage applied between the collector and base contacts. And then we express the current in the diffusive form. Jn is QdC times the derivative of n with respect to x. And we have a minus. We have a minus. Why? Because you remember all these solutions are linear combinations of positive and negative exponentials, okay? And then we eliminate one of the two using the asymptotic condition. Now, in the case of the collector, the asymptotic condition is at infinity. So we must eliminate the exponential with the positive exponent, and then we keep the exponential with the negative exponent, okay? But immediately after that, we find that Jn of OC plus is equal to minus Q dC and C over LC times FC. So we have a minus sign, okay, which looks odd. We shall fix this minus sign later because at some point we remember that whereas the emitter current is aligned with the x-axis because the emitter current enters from the left, the collector current enters from the right, so it is opposite to the positive sign, the positive direction of the x-axis. So at this point, we shall fix the minus because of this. Okay, so there is nothing to worry about. Fc is again a dimensionless factor with the exponential of Q over KT times VCB minus 1. So this is it for the emitter and the collector regions. Now we go to the base region. And the base region in the PNP device is doped of the N-type. So the minority carriers are holes. So we must consider the holes in the base of the PNP transistor. So we are between OE plus, and here we can place the 0. And the other side of the neutral base region is at OC minus. And OC minus is at the finite distance from the origin. And actually, we know this finite distance is W, is the width of the neutral base region. Okay. Then the equation reads like this: second derivative of P minus PB. PB corresponds to Pn0 of the p-n junction, and it is calculated as Ni squared over Nb. And Lb is the diffusion length of the holes in the base region, okay? Now, when we apply the boundary conditions, we have to apply the Shockley conditions on both sides because there is no asymptotic condition. So we must say that P at 0 is equal to Pb exponential of Q over Kt VEB, whereas P at W is equal to Pb exponential of U over Kt times VCB. Okay, so the two boundary conditions embed the two voltages, the two independent voltages that are applied to the device. The solution has the form P of x minus the constant Pb is equal to the linear combination of two exponentials, one with the negative side and the other with the positive side, and the two constants of the linear combination are generally called A and B. And we cannot eliminate any of them because there is no asymptotic condition. We can simply apply the two Shockley boundary conditions that are indicated above. So when we fix x equal to 0, then we find that the left-hand side of the solution provides Pb times f of v because we have the exponential minus 1. And this is equal to the right-hand side of the solution calculated at 0. So it is A plus B. Then we have a second relation found by letting x equal to W. So in this case, the left-hand side of the solution becomes Pb times f sub c. And the right-hand side becomes A times the exponential of minus WLB plus B exponential of WLB. Now you see that we start seeing the ratio W over LB. So this is why it is important to be able to compare the length of the base neutral region with the diffusion length of the minority carrier. You see immediately that the ratio W over LB is important. In conclusion, the boundary conditions provide two algebraic equations in the unknowns A and B. It's just a 2x2 algebraic system to be solved. It is very easily solved because if you multiply the first equation by the exponential of W over LB, and then you subtract the second equation from the first one, you obtain that 2 times A, you see it near the arrow below. 2A times the hyperbolic sine of W over LB is equal to Pb Fe exponential of W over LB minus Pb times Fc. So we have an expression in which everything is given, is known apart from A. So we can calculate immediately A. If instead we multiply the first equation of the boundary condition by the exponential of minus WLB, and then we subtract again the two equations, we obtain an expression for B, and this expression again has this hyperbolic sine of W over LB, and then the other term on the right. Given that we have calculated A and B. And that means that if you look up a little, we know the behavior of P of X inside the neutral region of the base, because now we know the two coefficients A and B. At this point, we can take the derivative in order to calculate the current density, using, again, the diffusive. The diffusive part of the current. So the diffusive form of the current density for the holes as a minus. So we have minus Q dB times the derivative of P with respect to X that is taken from the upper expression. And we have this formula here in which A and B are known. Then if we let X equal to 0, remember 0 here coincides with OE plus. Then we obtain Jp of OE plus, and this is given by this rather complicated expression here. So J of OE plus is a coefficient that is QdB PB over LB times a term in which we have Fe multiplying the hyperbolic cotangent of W over LB minus the other term Fc divided by hyperbolic sine of W over LB. You remember F sub E and F sub C contain the applied voltages, the exponentials of the applied voltages. In the same manner, we can calculate the minority carrier current at OC minus, that is the right edge of the neutral base region. We simply impose that X is equal to W, and we obtain Q dB PB over LB times a quantity in which we have the two terms F sub E, F sub C. The first is divided by the hyperbolic sine of W over LB, and the other multiplies the hyperbolic cotangent of W over LB. So we have these two expressions. How do you proceed? We proceed exactly as we did in the p-n junction alone. At each junction, the total current density is equal to the current density of the minority carriers on the left plus the current density of the minority carriers on the right plus the recombination current density over the space charge region. So we simply put down this expression. When we calculate this quantity at OE minus is inside the emitter. So eventually the result of the first calculation will be the emitter current density of the device. Obviously, the emitter current density is equal to the current density of the electrons plus the current density of the holes at the same position, OE minus, for instance. Jn of OE minus belongs to the minority carrier, so it stays. Jp of OE minus is a majority carrier current density, so we replace it with, as we did in the p-n junction, with Jp of OE plus, that is again a minority current concentration, plus the recombination current associated to the emitter junction, okay? For the moment, we do not consider the last term, it will come later. We observe that we have the expressions for the first two ingredients. We know Jn of OE minus and Jp of OE plus. We simply replace the expressions and extract Fe and Fc, okay? Then we do the same on the other side, in the collector, okay? In the collector, when we consider the total current density, of course, is the total current density of the collector. So eventually this operation will provide us with the current of the collector. Again, we start at OC plus. We calculate the current as the sum of the two electron and hole currents. Then Jn of OC plus is the minority current density, so it stays. Jp of OC plus is replaced with Jp of OC minus less the recombination current associated to the collector, okay? Then for the moment we put the recombination current aside, we calculate the other two terms. The other two terms actually have been calculated already. So we put them together and we obtain these two new expressions for the collector current density. And again, we extract Fc and Fe, okay? You remember, in these last expressions, the terms with the cotangent, the hyperbolic cotangent or the hyperbolic sign derive from the base. Instead, the simpler term here, dE and E over LE, comes from the emitter, and dC and C over LC comes from the collector, okay? At this point, we give names to all these coefficients, okay? So the coefficient that multiplies F sub E in the first equation, this quantity, first is multiplied by the cross-sectional area of the transistor. In this case, the cross-sectional area is called A sub E because A was one of the coefficients, okay? So we multiply by the area, and then we have Q times the area times the parentheses. Of course, you see, number one, that this term that to which we give the compact name A11, A11 is strictly positive because it's the sum of terms that are all positive. And also A11 has the units of the current because Fe is a pure number because it is an exponential -1. The coefficient before it gives a current density. So this coefficient here, Q times the square brackets, is a current density. If we multiply by the area, we obtain a current. So A11 is a current. Then we do the same for the other coefficient in the second equation that multiplies Fc. This coefficient is multiplied by the cross-sectional area again, and it is called A22. We don't incorporate the minus sign in the definition, so This term is strictly positive also. A22 is strictly positive. Then we have other two terms. One term is this. It is the term that multiplies Fc in the first equation. And then we have the term that multiplies Fe in the second equation, okay? So again, we multiply this, you see it is the same. It's the same term. Q dB PB over LB divided by the hyperbolic sine of W over LB. So we define it with a minus. And we call it A12, the first of them, the one that multiplies Fc in the first equation. And finally, the other term that multiplies Fe in the other equation is identical. We call it A21 just to distinguish, but it is identical to A12. Okay. One question, do these terms A11, A22, A12, etc. depend on the bias? The answer is yes. They do depend on the bias because they contain W. W is the extension of the neutral region of the base. And if you go back to the figures, this one, for instance, W is the distance between OC minus and OE plus. If you change the bias on this junction, you move OC minus. You change the position of OC minus. You remember, because the width of that region depends on the bias, especially when we are in the reverse bias condition. Similarly, if you change the bias on the emitter junction, you change the position of OE plus. So W does depend on the applied biases, okay? And through W, all these coefficients depend on the two biases, okay? So, but we hope that this dependence has little influence, okay? We shall see that indeed there is a not so important influence of this dependence on the current of the bipolar transistor. Conclusion. With these symbols, we define the total current of the emitter, including also the recombination current density, because you see there is OE minus and also OE minus here. JN and JP are both calculated at OE minus. So this is the total current of the emitter. Then we define separately a symbol for the recombination current of the emitter junction, EUE. It is the integral of QU times, extended over the space charge region of the emitter, multiplied by the cross-sectional area. So this is the recombination current of the emitter. If we now take the results of the calculation of the previous page, we find immediately that the emitter current can be expressed as A11FE plus the recombination current plus again A12FC. We shall see in a minute how to interpret this expression. Now we go to the collector. You remember we anticipated that the current of the collector enters the collector from the right. So the direction of this current is opposite to that of the x-axis with respect to which we performed the calculations. For this reason, we must now define the collector current with a minus. So we compensate for the minus that existed at the end of the previous calculations. We also define IUC, the recombination current of the collector, as the integral extended in this case over the collector space charge region times the cross-sectional area. Using these definitions, we have an expression for IC, the collector current, that is the one given here, A21FE plus A22FC plus IUC. Let's try to interpret this result using equivalent circuit, okay? You remember we are using the base contact as the common contact. So this is also called, as you may remember from other classes, this is the common base configuration of the bipolar transistor. The base contact is the reference contact, okay? So if we want to represent the device as a double bipole, we must prepare a figure like the one that is shown in the lower part of the page, in which we have on the left the two contacts VEB, of emitter and base, to which the VEB voltage is applied, and the emitter current is entering the device. Now, if you look at the formula on top, you see that the emitter current, actually the formula of E sub E that is near the arrow, E sub E is the sum of two blocks. One block is the block in parentheses, A11FE plus IUE. And then we have a second block, A12FC. So in circuits, when a current is the sum of two currents, it must be represented, as you remember, as two branches in parallel. So in fact, in the figure, you see that the total emitter current becomes two branches, okay? The branch that is below, the one with the diode and the indication IED, is the term in parentheses. Why? Because if you look at it, you have a coefficient time exponential of U of Q over KT times the applied voltage plus the recombination current. But this is exactly the form of the expression that you obtain from a PN junction, exactly. Of course, the coefficients are different and the symbols are also different, but this is exactly the current associated to a diode subjected to the voltage VEB. So we call it IED, the part of the emitter current due to a diode. And in the circuit, it is represented in this form because you see the two nodes, the two contacts of this diode are subjected to this voltage VEB. and the diode is, through the diode we have the current IED flowing. Then we have the other branch in parallel. The other branch is due to the term A12FC. But FC depends on the voltage on the other side. Depends on the, if you remember, depends on VCB, on the collector voltage. So this branch that we indicate with the symbol IEG is a current that is controlled by a voltage that is not the same voltage applied to this port of the device. It is a voltage from some other place in the device. So this branch must be thought of as a controlled current generator, a current generator controlled by a voltage. Okay, and this is why in the circuit it is indicated with this symbol, and the symbol is IEG, the part of the emitter current due to the controlled generator. Okay, we stop here now. We shall resume again at 6:10. Okay, so we start again. Before we start the technical part, I just wanted to mention that the last hour that we just completed a few minutes ago was number 30. So technically, that was the last hour of module 1. I'm telling this to the benefit of those of you who has decided to choose module 2 as elective. Okay, so it is implied that these students already had the knowledge of the subject of module 1. Okay, actually, in order to complete the subject of module 1, we are still missing the MOS devices. It will take a few hours, okay, for those, but technically we are now starting module 2 of this course. So let me share the screen. We just described the emitter current. If we repeat the analysis for the collector current, the analysis is just identical. The collector current is made of the sum of two blocks. So in a circuit, it must be represented as two bipoles in parallel with each other. One of them, that is called ICD, is the portion of the collector current of the diode type, and it is the quantity in parentheses A22FC plus IUC. So it is a diode proper controlled by the voltage VCB applied to the two contacts of the diode itself. The other branch in parallel to it, that is called ICG, is a current that is controlled by the voltage applied on the other side. It is proportional to FE, so FE depends exponentially on VEB. So ICG also is a voltage controlled current generator, okay? So you see that the structure of the equivalent circuit is symmetric, but the numbers are non-symmetric. So the coefficients are different, everything is different, okay? The only thing that is equal is that A21, coefficient A21 is equal to coefficient A12, okay? But the other coefficients are different. Let's take some limiting case. You remember, we started saying if somebody has designed a bipolar transistor in the wrong manner by taking W larger than LB, so this is the wrong design. Okay, let's see what happens in the equations. Well, of course, we have to look at the coefficients because the coefficient, as we already noted, depend on the ratio W over LB. Okay, so the coefficients are A11, A22, A12. So A12 is the easy one, because if W is much larger than LB, then the hyperbolic sign grows exponentially, and it is in the denominator. So when W is much larger than LB, the coefficients A12 and also A21 disappear. But if you look at the equations here, if you kill A12, it's like killing IEG. And if you kill A21, it's like killing ICG. So you kill the two generators and you are left with two diodes, one in front of the other, as we noticed at the beginning today, okay? Also, again, when W is large with respect to LB, we also have a limiting case in A11 and in A22, because we have the hyperbolic cotangent of W over LB, okay? So you remember the hyperbolic cotangent is the hyperbolic cosine over the hyperbolic sine, okay? So when they grow both exponentially, the ratio goes to 1. So the cotangent goes to 1, and A11 becomes exactly the coefficient of the p-n junction on the emitter side alone. And A22 becomes exactly the coefficient of the p-n junction on the collector side alone. Okay, so we have exactly the limiting case that we expected, but this is of no interest, okay, because of course, if W is larger than LB, this is the wrong design. In actual situations, it is the opposite, because maybe you remember that a couple of days ago, we analyzed the orders of magnitude of some quantities in the p-n junction. Okay, this is it. We found out that the diffusion lengths are large, like 360 microns in this example, or 160 microns in this example, okay? In real bipolar transistors, W, that is the width of the neutral phase region, is about 1 micron. So not only it is not true that W is much larger than LB, actually W is much, much smaller than LB, okay? We have about 1 micron for W and about 100 microns for LB or more, okay? At this point, we can take the other limit. So we can approximate the exponentials in the case where the exponent is very small, much smaller than 1. Okay. So again, let's take A12. When you consider A12 and you have that W is much, much smaller than LB, you remember the hyperbolic sign when the argument is very small, much smaller than 1 in modulus, behaves like the trigonometric sign. So the hyperbolic sign of a small argument is practically equal to the argument itself. So that means that sine the hyperbolic sign of W over LB is just like W over LB. And LB cancels the other LB, okay? So we are left with dB PB over W. When we consider the hyperbolic cotangent, the hyperbolic cotangent is the hyperbolic cosine divided by the hyperbolic sine. So in the denominator, the hyperbolic sign, when the argument is very small, behaves like we have said just a second ago. We have that the denominator LB here is replaced with W. Then we have the hyperbolic cosine in the numerator, but the hyperbolic cosine, you remember, is second order in the argument when the argument is very small with respect to 1, so we neglect it. It's like having 1 minus W over LB squared. Okay, so we neglect the second order term and we have 1 instead of the hyperbolic cosine. It is just the same as for the trigonometric functions, okay? So in the reasonable limit in which W is actually much smaller than LB, we have a much simpler form of the coefficients, okay? So you see we have W here instead of LB. Again, we have W instead of LB, and again here and there we have W instead of LB. Okay? Can we go on in the simplifications? Yes, because you remember we distinguished for the bipolar transistor 4 operation regions, okay? Saturation, normal, inverse, and off, okay? We do not consider the off region, the off state, okay? Because simply the two junctions are in the reverse bias and there is little current in them, okay? When we consider all the remaining 3 operation regions, saturation, normal, or inverse, there is at least one current that is large because at least one of the 2 junctions is forward biased. When there is one current that is large, okay, the other current also is large. So if the emitter current is large, we shall see in a minute also the collector current is large, okay? So if these 2 currents are large, those associated with the exponentials, then we can neglect the recombination currents. So we consider the functioning regimes in which IUE here and IUC here are negligible. Okay? So we don't consider them anymore. Thanks to this, we can formally express the relations between the currents and the voltages of the bipolar transistor as it is typically done in the circuit theory as a double bipole. A double bipole is described, as you see on the left, as the 2 currents, emitter and collector currents, given as a function of the 2 voltages. And the 2 voltages are embedded in the terms FC and FE. that are of the exponential form, if you remember. Besides, at some point you may say, but we also have a base current. The base current is just the algebraic difference of the two. You remember, due to the Kirchhoff law, the sum of IE plus IC plus EB, if IB is taken as entering the base, must be 0. Okay? So IB is the algebraic sum of the other two currents. Okay, so it is not an independent current. We can calculate it after calculating independently IE and IC. Okay, so the consideration of the two currents IC and IE is sufficient. Okay, so we have a double bipole in which each current of interest is represented in terms of the two applied voltages. Okay, probably you remember that in the circuit theory for the bipolar transistor, it is also convenient to use another representation that is called mixed. In the mixed representation, the emitter current is still expressed as a function of the two voltages, VEB and VCB. Instead, the collector current is expressed as a function of VCB and IE. So it is expressed as a function of one of the two voltages, in particular the collector voltage, and the emitter current. Okay, so how do we go from the representation that is indicated on the left to the representation that is indicated on the right? It is actually very easy because the representation is linear in the exponentials Fe and Fc. Okay, so we simply eliminate Fe from the equations. Okay, so from the first equation, the one that describes the emitter current, we extract Fe, and it turns to be equal to IE minus A12Fc divided by A11. Then we do the same from the second equation. In that case, F sub E is equal to IC minus A22Fc, again over A21. And these two quantities must be equal. So by putting them equal to each other, we eliminate Fe, and then we extract IC. So this formula here, that is rather long, okay, is actually IC expressed in terms of VCB. VCB is inside this FC, and IE, okay. Now we consider the coefficients, okay. Obviously, the coefficient A21 divided by A11 is a pure number, because IC is a current and IE is also a current, okay? Also, you remember A21 is negative and A11 is positive, okay? So we give it a name, we call minus A21 over A11, we call it HFB. So the first term of this equation turns out to be minus HFB times IE. HFB takes a name, is called the gain, the current gain of the bipolar transistor. This is a steady state analysis, so it is a current gain in steady state when the transistor is in the common base configuration. So the second index, B, reminds you that we are in the common base configuration. The first index means forward, okay, because we are connecting IC with IE. And in order to remember that this quantity is calculated in steady state, the two letters F and B are in capital form, okay? In small form, they would be dynamic conditions, okay? Capital letters means steady state, okay? Let's analyze a little bit more the gain, okay? Because you expect that a gain should be larger than 1. Actually, it is not, okay? So this gain, HFB, is found simply by replacing the expressions of A21 and A11. So it turns out to be equal to a fraction in which the numerator is 1 and the denominator is 1 plus some positive quantity. So obviously, HFB is between 0 and 1, okay? For the moment, we do not analyze it further because we need to analyze the second part, okay? When we go back to the expression of IC, we have a second term that comes again from the elimination of FE, okay? And this second term must be, it is A11, A22 minus A12, A21 divided by A11, okay? It must be a current because FC is a pure number, okay? We call it IC0, okay? Why it is called IC0? Because if you look at this formula, IC is equal to minus HFBIE plus IC0FC. And you consider the normal mode of operation of the bipolar transistor. You remember, in the normal mode of operation, the emitter junction is forward biased and the collector junction is reversed biased, okay? So FC, we go back by a couple of pages. FC in the normal mode of operation has a negative value of the collector voltage in the exponent. So, and it is typically large, okay? So when you put a large negative number here, like 1, minus 2 volts, the exponential becomes immediately negligible because you remember Q over KT is about 38 volts to the minus 1 at room temperature. So FC is equal to minus 1, okay? FC is equal to minus 1 in the normal mode of operation, okay? So this formula here, in the normal mode of operation, becomes IC equal minus HFBIE minus IC0, okay? The minus sign is easily fixed because when you consider circuits instead of devices, okay, it is typically assumed that the emitter current, instead of entering, sorry, the collector current, instead of entering the collector, exit the collector. So what you do is just you reverse the sign of this equation. Assume for a second that you have IC prime, that is the negative IC, equal to HFBIE plus IC0FC. Okay. Now, if you now replace all the expressions of the coefficients small a, 1, 1, a, 2, 2, etc. into definition of the IC0, you find that IC0 is positive. Okay. Assume for a moment that IC0 is small, so that the part related to IC0 is negligible if the other term is non-zero. Okay, so you have IC prime, which is the negative of IC, equal to HFB IE. So this explains why HFB is called gain. Is the ratio between IC and IE, okay, in the bipolar transistor functioning in the normal mode of operation. Instead, you may consider a situation in which the emitter contacts are left open, such that IE is 0, okay? So this expression becomes IC equal to IC0. So this explains why, still in the normal mode of operation, this coefficient here is called IC0. It is called IC0 because it is the value of the collector current in the normal mode of operation, meaning when we have a negative voltage on the collector, when the emitter contact is left open. So when we don't have any current in the emitter. Okay, of course, the only current that is left is IC0. Okay, so given that, let's now go back to the gain. Okay, what we need is that the gain HFB, which is by construction a number between 0 and 1, we want it to be as close to 1 as possible. Okay, what we want is that the collector current be as close as possible to the emitter current, which from the practical point of view means that when we bias the device in the normal mode of operation, the emitter junction is forward biased, so we inject a lot of current into it. This current crosses the thin region of the base. A few of the carriers recombine and provide the base current, but the majority of them will be able to cross the base region and enter the space charge region of the collector. At this point, the field in that region will drag all these carriers into the collector, and they will form the collector current at the other end of the device. Okay? So what we want is to have the majority of the particles that are injected from the emitter to exit from the other side from the collector. And this is achieved if the gain HFB is very close to 1. So in order to make it very close to 1, what we have to do is to make the coefficient in the quantity in the denominator of HFB as small as possible. Okay? So let's do it. Let's do it. You see immediately that in this ratio we have N sub E, that is the concentration of the minority carriers of the emitter, that are the electrons, divided by PB, that is the concentration of the minority carriers of the base, that are holes. Okay, we want this number to be very small. NE over PB must be much smaller than 1 in order to have a gain as close as 1 as possible. But you immediately see that if we replace Ne with the expression Ni squared over Ne, that is the dopant concentration of the emitter, and we replace Pb with Ni squared over Nb, we obtain that the ratio that we want to be small is capital NB over capital Ne. So it is sufficient that we dope the emitter much more than the base in order to have Ne much larger than Nb, and we have this ratio much smaller than 1. So the explanation now, why do we dope the emitter much more than the base, is in order to get a current gain as close to 1 as possible. Okay? Of course, we can play also on the other parameters, but W is fixed by the technology and LE is also fixed, okay? W is much smaller also than LE, okay? So this is another good point, okay? What about the diffusion coefficients? Well, you see immediately that D sub E is proportional to the mobility of the electrons, because they are the minority carriers in the emitter when you consider the PNP transistor. And dB is proportional to the mobility of the hole. So this ratio is larger than 1, because the mobility of the electrons is larger than the mobility of the holes. So if we take, instead of the PNP transistor, we take the NPN transistor, we reverse this ratio, and the gain is even better. It's even closer to 1, okay? So the fact that IC in the normal mode of operation is practically equal to IE explains why we could neglect both recombination currents, because E sub C is large even if the bias in the collector junction is reverse, okay? And this also applies with some modifications to the inverse behavior or polarization of the device. So we came to the explanation about why the dopant of the emitter must be larger than that of the base. Now we must explain why the dopant of the base must be larger than that of the collector, okay? But this is easy. We go back here. When you consider the normal mode of operation, the edges of the space charge region of the emitter junction don't move very much if you change the bias, because you are in the normal operation mode, you are in this junction is in forward bias, okay? So the positions of OE minus and OE plus don't move, don't change, okay? The other junction is in the reverse bias condition. So the two edges, the positions of the two edges, OC plus and OC minus, do change, okay? And if OC minus change, then W will also change, and you don't want it because there is an unwanted, indirect, and difficult to calculate influence of the bias on W, okay? So the reason why you introduce a dopant concentration of the collector much smaller than that in the base is simply because in this case you have that OC plus will move essentially, because this is the lightly doped side of the region, okay? So OC minus will have a distance from the junction so small that even if it changes, it will change very little, because most of the changes in the width of the depleted region will go on the right-hand side, on OC plus, okay? And of course, if you have a light doping concentration in the collector side and you have OC plus very large, then impact ionization will be prevented, as you remember, okay? Because typically the collector junction in the bipolar transistor is reverse biased, and you have a danger of impact ionization. So this is it for the bipolar transistor. Here it is just indicated that in circuits, you take the collector current not entering the collector but exiting from the collector. So you take IC prime equal to minus IC. So you repeat the calculation by reversing the signs of the equation. But this is enough for the bipolar devices, apart from one consideration. Likely, if you have followed the explanations in some other class about the bipolar devices, you may remember that typically the equivalent circuit of the bipolar transistor is given using just one generator and not two generators, okay? So it is very easy to manipulate the circuit having two generators in order to obtain a circuit with one generator, okay? So we need the equation, so I did the wrong thing. I must rotate again. You can go from the circuit having two generators to another circuit that is fully equivalent, having only one generator, by a simple manipulation of the formulas. You remember IE is the sum of two currents. One is a diode-like current and the other one is a current generator current. Now, you remember that A12 is equal to A21, okay? So you can simply add A21 Fe to this formula. And then you subtract A21 Fe again, so it is an identity. Then you remember that A12 is equal to A21, and you write it in this form. Then you do the same with the collector current. In this case, you add A12FC. So A22FC becomes A22 plus A12FC, and then you subtract it, and then you replace A12 with A21, okay? So you have two equations in which now the last term is identical, apart from the sign, okay? Now introduce some modifications in the definitions. The first block in the square brackets in the first equation, again, is the current of a diode, okay? Some coefficient times the exponential -1 plus the recombination current. Call it IEDR, just a name for this quantity. In the second equation, again, the brackets is a diode, is the current of a diode. Call it ICDR. And finally, the common expression here, call it IG. G stands for generator, okay? So if you put the equations in compact form, you find that IE on top is IEDR plus IG. And the second current IC is ICDR minus IG. So now we need to find an equivalent circuit for these two equations, okay? But this is very easy again. Each current is the sum of two currents, so it is a parallel of two terms. The first term is a diode that depends only on the voltage of the same port. The second term is a current that is in parallel, and it is the same current for both, okay? So now we can go to the figure. And if you look at the circuit on the upper left, you see that this circuit exactly reproduces the new equations because IE is the sum of a current IEDR of a diode plus a current of a generator. And this current goes from left to right, so it is like this one. So IE is the sum of the two. IC has two parts in parallel. One part is ICDR that enters, and the other part is again IG, but IG comes from left to right, so IC is the difference. So this justifies the minus sign, okay? So this is simply the circuit of the bipolar transistor with only one generator. You may be accustomed to see the equivalent circuit instead of using the common base configuration. You may be more accustomed to use the common emitter configuration, but this is just a matter of magic on the circuit, okay? You just deform the circuit. If you look at again on the left, it is the same as above, but the contact of the emitter has been elongated upwards and downwards, okay, to better evidence the new voltage VEC. And also the collector contact has been simply elongated graphically upwards, okay? Now, if you want to go to the common emitter configuration, you must take the emitter as the common contact so that the two independent voltages will be VEB and VEC. So consider this figure on the left as rotated by 90 degrees to the left, and then you mirror it along a vertical axis, okay? So you go from this drawing to this other drawing here It is just the same, simply rotated and mirrored, okay? So you have the common emitter configuration, IB here, IC there, one single generator, and two diodes, as before, okay? From this circuit, you remember, of course, in circuit theory, when you need to consider the small signal analysis, then you linearize the devices, okay? So when you linearize a diode, you obtain a resistor, okay? And this resistor is typically called R sub pi, okay? And when you linearize this other diode, you obtain another resistor that is called R sub mu, and it is usually neglected because R sub mu is very large because that diode is biased in the reversed mode, okay? So this is how you obtain the small signal equivalent circuit. If you have a dynamic analysis and you need the capacitances, then you add the capacitance of the vertical diode, and you remember you call it C pi, and the other one will be C mu. Okay, the two capacitances that are used in the dynamic analysis of the bipolar transistor. Okay, there is only one thing left, that this analysis refers to a completely one-dimensional device. You remember, which is rather unrealistic because the base current flows laterally with respect to the device. So this is fixed qualitatively by adding a series resistance to the base, okay? And that series resistance somehow accounts for the voltage drop that is intrinsic to the base because of the flow of current laterally into the base. So the intrinsic base resistance that is not shown in this figure, and it is not RB in the next figure, okay? This is outside, not intrinsic, okay? The intrinsic base resistance accounts for the lateral flow of the base current that is not considered by this model, okay? So this is the completion of the material related to the bipolar transistor, and tomorrow afternoon we shall start with the MOS devices. So if there are questions, you may ask them now. Okay, thank you.